hell yeah. So this is part 4 of this problem, you know what I mean? And it's just kind of my 4th go at it. And so what we're going to tackle is this question B. It says, obtain the expression for the equation of trajectory. And I had to look this up. I'm just like, what the hell does that even mean? And it's kind of interesting when you're doing like, you know, free-falling mass problems or I guess trajectory problems where you have like a parabolic shape. And it's fascinating because what this says is get an equation. So this is going to be like, just pretend like the looking at this cliff sideways, you know what I mean, like looking across the horizon and seeing this ball shoot off this cliff and fall. Well, you can think of this as just an XY graph, and I just want the equation for the line that it makes. You know what I mean? If this traced out a line, I want that equation. And it's just like, oh yeah, no duh. You know what I mean? And that equation, it can be represented 2 ways. Typically, it's going to be represented as y equals x, where x is my independent variable. When x is 0, I know it's going to be at the top of the cliff. And then when x is, you know what I mean? Well, and then it's fascinating from free fall because we're going to get we get all the equations as a function of time. And then so I can throw in this height of this cliff and then know how long it's going to take to hit the bottom. And we're going to get 2 equations that are independent of each other. This y equation, you know what I mean, for gravity pulling it down, and even in this problem has air resistance resisting that. But it's going to take some amount of time to hit the bottom. Irrespective, or it doesn't really matter what the velocity of this thing. You could just drop this ball off the cliff right here, or you could give it 100 miles an hour speed, and it's still going to take the same amount of time in the y direction. So, but once we can get that time, then I can say, well, that's going to be the same time for the x equation. So I'm going to get an equation. I know this thing has, you know, constant velocity coming off, and if air resistance was negligible, I would just know it's just that velocity times the time, and that's going to be the distance that it hits. So there you go. So even on my graph, I would at least know 2 points. When x is equal to 0, y is equal to this height. And then when x is equal to this distance, y has to equal 0. So if I do get an equation for y equals x, I can double check and just make sure that those 2 jive. Okay, hell yeah. And then, but doing this, you're going to have to, I mean, because we have air resistance, like both the x of t and y of t equations, they're fairly complex, especially this y of t. And then so if we're going to combine them together and, you know, get rid of the t component, then we might just make algebraic mistakes. So this video is like, hey, how can I go about this so I can guarantee that I have a right answer? So what we're going to use is Excel. And this is part 4. We already went over the y direction. We said that in the y direction, we're going to have acceleration. That's going to be, the acceleration is going to be 10. Let's see what we have here. The acceleration of, what's this acceleration equation? So, okay, yeah, here we go. So because if we didn't have air resistance, the acceleration is just gravity. It's that 10. So, and what that means is that every second, I'm going to increase my speed by 10. So 0, 10, 20, 30, 40. So why aren't these 10, 20, 30, 40? Is because we have air resistance. And this is the simplest way to show how forces cause acceleration. And for this problem, they just give you the acceleration. They say that gravity is an acceleration of 10, kind of, and I'm just going to assume it's kind of like, my equation from this is going to be backwards to what the problem wants, because they want this to be the y positive. I got into a huge hiccup. We crossed that barrier, but the algebra was destroying me, and so I had to just do this in this positive direction. And then when I did so, I was able to algebraically do the calculus to match these equations. But now today I know what I did wrong, and so I can say that this acceleration would be negative 10 plus whatever. And even if I just, yeah, so, but I'm not going to change that right now. So just keep in mind that's the only deviation that I'll have. Okay, sweet. So yeah, so this acceleration is going to be 10, and then minus the air resistance. And what they want us to use for air resistance is this equation. Whatever the velocity is, we're just going to multiply it by some sort of constant. And so for problem D, they're just going to say that constant's 0.005. And it's inverse seconds because when we multiply it by velocity, then the units on this are meters per second per second. That's going to be a change in velocity, change, in meters per second every second. Cool, and so that's what this acceleration represents. When our velocity is 0 at the top of the cliff, multiplying by c, this value is just 0. So we just get the acceleration as 10. Right here, though, we're going to have, after we get an acceleration of 10, then we're going to go 10 times 0.05, and hell yeah. So then we would get, what would we get? 0.5. And so we're not going to increase by 10 meters per second in that second. We're going to increase by 9.5. So our velocity is 10, and then we only increase by 9.5, so our new velocity is 19.5. And then hell yeah. So if I know my velocity between 0 seconds and 1 second, what I'm going to do is get my average velocity. So hell yeah, that average velocity is 5. And then I know we traveled for a second, so I know that I traveled 5 meters. Yeah, 5 meters. And then so forth. Okay, and then I just refine that by changing my change in time to be an increment of 0.1. You know what I mean? So my acceleration is still the same, but then my change in velocity, because acceleration is change in velocity divided by the change in time. If I have a 1 second change in time, this is my change in velocity. If I only have a 0.1 second change in time, look at this. I'm taking the acceleration, and then I'm multiplying it. So acceleration multiplied by this change in time is the change in velocity, because this is the equation. Let's look at this equation for acceleration. Acceleration is change in velocity divided by change in time. If I wanted to solve for the change in velocity, I just multiply it by that change in time component. Cool. And then so what we get is that, and let's throw some, and then we do it again with a time frame of 1/100 of a second. And then we can see that the thing's going to hit the ground at 500 feet. If it's at the top of the cliff, it's going to reach 500 meters, at 10.91 seconds. And right here, if we go to 500, hey, there's 10.9. So booyah. And if we go right here, let's see what this one was. So this one, hey, we reach 500 between 10 and 11 seconds, but it looks like pretty closer to 11 seconds. Okay, so now we have a check on reality there. So what we're going to do is I'm going to now say this is the, and, oh, it's fascinating. I even have an x value on this. This should be y. Like, that's the y direction. Yeah. So we have, you know what I mean? So on our picture, we were trying to find the change in velocity in the y direction. So sometimes just generically you're just using the variable x, because change in velocity is usually be dx dt, but that's just, you have to choose what direction that is. You can choose whether x is the vertical or the horizontal, but typically x is going to be the horizontal. So so these equations are dy, but because of that, this would change to y. So yeah, let's get this at least squared away. So this would be a change in the y, and there you go. So my y value is 0, and like I said, I'm deviating from the problem. I'm saying my coordinate system is right up. I'm saying my coordinate system is right here at 0, and it's positive in this direction. So, yep. So I would have to redo this to make it fit the problem statement. But cool. And then there's an X right there. Change that to Y. Okay, so I think we're looking good over here. So what we're gonna do is now have we're gonna do this in the X in the horizontal direction. How about that? So what we're going to find is that this thing is going to fly off the cliff with some sort of speed. And they say that initial speed is u. It has two components. It's a vector. It's got a component in the x, v of x, and a v of y. When it flies off this cliff, it doesn't have a v of y. V of y is 0. But v of x is u. So, cool. So, hell yeah. So the initial velocity, and let's just give it some velocity. Let's just give it 100 meters per second. Cool. And then what's the acceleration? Well, if it didn't have air resistance, it would just continue at that speed. It would not slow down. The acceleration would be 0. And we would just have a pretty simple equation to deal with. But because we have air resistance, the air resistance is going to be equal to, so the air resistance, so we're going to have some positive velocities. That's why I'm just saying the downward, well, no, in this case, we're saying this is the positive direction. So cool, we got some positive velocity. The air resistance is going to change that velocity and slow it down. So this term is going to be negative, and it's going to be negative. It's going to be this constant times the velocity in the x direction. Cool. So, and that's going to be in units of meters per second. So every second, we're going to slow down 5. So now I even know, so, and then here we need to go to this equation, because when we try to refine this, you know, we're just doing in increments of a second, and this is very useful. Like I can just literally say this is 100 plus this acceleration. But when we change this interval and try to get a little bit tight, we need to use this equation, that the change in velocity is the acceleration, so it's going to be equal to this acceleration multiplied by the change in time. So we're going to have this time minus this time, and that's just 1 second, so nothing changes there. But now this is my change in velocity, and so I'm going to say this is the original velocity plus the change in velocity. Cool. Now I know between 0 and 1 second, I'm going to get an average velocity that's going to be equal to these two added divided by 2. And now this is my average velocity. And then what do we know about position? We say velocity is change in position, change in time, but this equation is average velocity. So I'm just going to read this one and then read this one. These are average velocities. So, yeah. Heck yeah. I don't think I want to read them. It's really difficult to see. All right, sweet. So anyway, and then just rearrange this. So the change in position is that average velocity times change in time. Let's try that out. So my average velocity times the change in time is this one minus this one. And booyah. And then I just have to make sure on this equation, this value won't change position. So I'm just going to come here and push F4. It puts $2 signs. So now when I drag it down, it won't change. Okay, hell yeah. So this is my change in position. So the original position was 0. And then our change in position is initial position plus our change in position due to that velocity in that direction. Hell yeah. And so now I can just pull this stuff down. And what we're trying to figure out is what's going to happen, how far away is it after about 11 seconds. And we can see that my position is 840 meters. No, maybe I messed up, but probably not. Because, no, like even right now I'm feeling pretty confident. Because if we go back to this, if I said there's no air resistance, this thing's going to come off at 100 meters per second, and it's going to take 10 seconds to hit the ground. The y direction, the time it takes to hit the ground, is independent of what the hell it's doing in the x direction. And if there's no air resistance, it's just going to continue at 100 meters per second. It's going to take 10, almost 11 seconds. This thing's going to go 1,000 meters. 1,900 meters if there's no air resistance. And because there's air resistance, this is going to get slowed down. And we can even do like a quick check on reality. You know what I mean? Let's say, and this is good even, I'm just going to say for you or whatever, but this is good for me all the time, is to be like, yeah, problems always, sometimes just constantly change. But forget about that, you know what I mean? Just figure out what it's doing right at the beginning. So this is a classic one where it's just like, okay, we're flying off at 100 meters per second, and our air resistance is a function of that velocity. 100 times 0.05 means that every second we're going to slow down 5 meters per second. And then so let's just say that's exactly what's going to happen every second. That's a fair assumption. Let's say every second we're going to slow down 5 meters per second, and it's going to take about 10 seconds to hit the ground. Well, it looks like we're going to slow down 50 meters per second. So by the time it hits the ground, our speed should be about 50. Is that a reasonable assumption? Hell yeah, it is. And then so let's say it's just linear, where our initial speed is 100, after 10 seconds is 50. So that means that we have an average speed of 75. And so 75 times, so let's just do, we'll come over here, equals 75 times 10. We'll just even do 10.9 seconds. So we should be at 817.5. This says we're 840. And hell yeah. So now that we know that would be a underestimate, because the air resistance is only big if our velocity is big. But because the air resistance is causing us to slow down, so now what you would do is just go to the halfway point. So let's say at 5 seconds, I slowed down 25. So 5 times 5 is 25. So now my speed is 75 after 5 seconds. So now what's my drag? Well, it's going to be equal to 0.05 times 75. So now I'm only slowing down 3.75 seconds. Okay, and let's say we do that for 5 seconds. So we're going to go this times 5. And sweet. So now I went from 100 to 75, and then we're going to go 75 minus that. So now my last speed should be 56.25. And so now we have 100, we have 75, and then we have 56.25. So what I'm going to do is I'm going to get my average velocity here, 100 plus 75 divided by 2. And then I'm going to get my average velocity for that next interval. And what we're doing is what you would do at like the first chapter physics, but I don't think anybody knows what's going on when they're doing like first chapter physics for the first time. And then once you do the integration approach, then you just never go back to those first chapter, you know what I mean? Like, what the hell's going on? And so, booyah. So this is the average speed for the first 5 seconds. So we're going to go this average speed times 5 plus this average speed times that next 5. And cool. And we're going to do 5.9 because, you know what I mean? We're basically going, well, let's just do 6, because if we're trying to match this time of 140, there you go. So now these two are fairly close together after 11 seconds. But let's hone this in. Let's say it's just 5. So booyah, 765. So this number is getting fairly close to that number. Okay, hell yeah. So now we kind of have a check on reality of what's going on. Okay, so what we're going to do is we're going to insert a bunch of cells. All right, hell yeah, so that's good enough. And I'm just going to recopy this. So I'm just going to copy and then paste. And then, ooh. Sorry about that. All right, so giving myself some room. We're going to copy this. I'm just going to copy it right here. Copy and paste. And then we're going to change this time frame to 0.1 seconds. And booyah, we're going to run it out to 10 seconds or 11 seconds. All right, looking good. My position is going to, and then so we have all our markers and our acceleration. But what changes is this value. See, my change in time is only, so after a tenth of a second, I'm only increasing in speed. I'm sorry, air resistance is decreasing my speed by 0.5. Instead of 5 meters per second, we just decreased by 0.5. Had this been 0.01, it would have been 0.05. And so now we're getting, just honing in and getting just more accurate. Okay, so let's burn this down. And then, yeah, let's see where we're at. Hell yeah. So at 10.9 seconds, we're right there. And so what we're going to do is let's see, because am I just going to use these two? You know, just increments of, I think so. I think let's just kind of keep it simple because we might make mistakes. So I'm going to insert a bunch of cells right here. Cool. And now what we're going to do is we're going to, so now what we have is we have our, and honestly, I've never done this, you know what I mean, so this is kind of the first time. Let me drink some water. But each of these, the time frame is the same. And so what we have is that, yeah, is this going to work out? Oh, darn, I don't want to pause this video. I thought I would just be able to do this pretty easy. So what we have is, at time 0, we have our coordinate xy. Yep, I actually have to pause this video. Sorry about that. All right, hell yeah. So I love when I just pause a video just for about like 30 seconds. And you're just like, oh yeah, no duh. You know what I mean? So what we're trying, like all we're trying to do is have a check on reality. So I'm just going to insert maybe one more cell here. I mean, what we want is a check on reality of x. You know, when I insert x, I want to know what y is. So here is the ball falling down the cliff in the y direction as a function of time from 0 to 11 seconds. This is its distance in the y direction. And so going 100 meters per second, you know what I mean, in a tenth of a second, it goes 10 meters. Cool. And then so forth. But drag is slowing it down. Booyah. So all we have to do is just like, hey, this is, and because these time frames are the same, at 0 seconds, its position is 0, 0. And so I'm just going to do this. And then y is this. And so that's all we're comparing is these two. And then so I'm just going to drag these down. Whoop, whoop, whoop. Oh, man. There we go. All right, hell yeah. So now when our x value is 839 meters, our y value is 500. Cool. And then the only thing about this is like, hey, if our speed is 50, well, obviously that's going to change the x value. And it's going to be about half, 422. So, but yeah, so that's the only thing that's kind of inconsistent. Our trajectory off the cliff is always with an angle of 0. So you could redo this problem and have a trajectory of some sort of, you know, like launch this cannon off the cliff and have air resistance. So that makes it just a little bit, it makes it, yeah, just more challenging. But booyah. So now this is it. This is our check on reality. This is, so now when I do the equation for y as a function of x, now I can throw in any value of x, you know, when my initial speed is 100, the top of the cliff is 500, and then we're using, So what we're using is basically this this problem D. I've already solved for in Excel, so I already know how long it's going to take to hit the bottom, and using this value for C, which is the coefficient that affects air resistance. The larger this is, the more the ball is going to slow down due to that air resistance. Cool. So yeah, so those parameters are all in here, but since it's all just in Excel, I can change my C value. I can change, and I have this set up backwards. So yeah, so maybe for the next video, we actually get this, you know what I mean, juiced around in the other direction, because obviously they want the height to be 500. So I'm going to have an input of 500, a value of C. My position in the Y is going to go from 500. That's going to be the initial position, I mean in the Y direction over here. So if it's falling off the cliff, this position would be 500 to start, and then we'd be going in the down direction. We go 500, you know, 495 or whatever. Cool. And even just to show what's happening right here, if I'm doing 1/10 of a second, acceleration due to gravity is 10. In 1/10 of a second, we're going to increase our velocity by 1 meter per second. We're going to go from 0 to 1. So we're going to have an average velocity of 0.5 meters per second. Sounds like we're going to go 0.5 meters, yeah, in 1 second. But if we're only going for 1/10 of a second, we're only going to go 0.05. So after 1/10 of a second, when you drop something, after 1/10 of a second, it hardly goes anywhere. 0.05, but that's still 50 millimeters. So cool. This is kind of cool. Now you have a check on reality even with you drop something and calculate its distance after 1/10 of a second. It's going to go a couple inches. So booyah, 50 millimeters. 0.05 meters. Okay, hell yeah. So, yep, so that I think I'm going to do that for part 4, is for sure just redo these, and we can probably do them fairly fast and maybe from scratch. So what I'm going to do is, you know, three things. I'm going to get the Y direction starting at a height of 500, and we're going to go this direction. My acceleration is going to be negative, you know, because we're picking up speed in the negative direction due to gravity, but air resistance is slowing that down. So air resistance is a positive change in velocity. Even though gravity is hella, you know, every second it's going to pick up 10 meters per second, and the acceleration due to air resistance is just a little bit, and it's a function of the velocity. And so that means that the acceleration, yeah, how does that work out? You know, I mean, if the acceleration is a function of the velocity, you get to a point where, let's look at this. So if the velocity, if this value becomes 10, because this is 0.05, and if we multiplied it by 200, if I got a velocity of 200 meters per second, my acceleration is 10 minus 10. My acceleration is 0. So we don't have any more change in velocity. And you can't have air resistance start, you know, like lifting you up or like slowing a skydiver so much they stop in midair. This acceleration just matches, and then, you know, so you have a driving negative velocity downward. Air resistance doesn't match it right away because it's a function of that velocity. Once that velocity gets up to 200 meters per second, hell yeah, then it's perfectly matched and you can't go beyond that. And as you're approaching 200, you know, your change in velocity is smaller. So, you know what I mean? It's almost like you actually never approach 200, but if you're just dealing with 3 significant figures, hell yeah, you'll approach it in about 50 seconds. And skydiving, you'll probably feel like you're approaching terminal velocity after about, well, even this problem, you know, if in this problem, you're going to be going 84 meters per second with that air resistance. Yeah, if this is a ball and the physics is right, you know what I mean, Now you need to go about 50 seconds to get up to 200 meters per second. So you're even after 10 seconds, you're not even close. But with the skydiver in full, their drag is going to be hella higher because you're in kind of that drag position, and then so your acceleration is going to be slower. It's going to slow you down a lot faster, and the top speed you're going to get to is only 50 meters per second, where you're going to get to 50 meters per second even from here. Like what does this say? You're going to get to 50 meters per second after about 6 seconds. So there you go. So now we have some just kind of general idea of maybe what a skydiver would feel, where this problem is a spherical ball, like a cannonball. And hell yeah, that's kind of fascinating. The drag might not be very much on a cannonball. And so it's going to have a pretty hella top speed at 200 meters per second. And it's going to take about 50 seconds to have that acceleration cancel. Okay, hell yeah. So we're done with, this is part 4. I don't know if I said part 4. But yeah, we'll do a part 5 where we rearrange these and get the negatives going in the right direction. So we have an equation that will be, that we can, basically here's our xy. So we'll get an equation, y equals x, and if we throw in any of these values of x, we can double check that if I throw in a value of 107, my value in the y direction is, and it would be like negative 5 point, so what would that say? If my speed is 100 meters per second, after 1 second, we drop about 5, and that's what we know from there's a lot of intuition, and this 5 is very, it's like, so if you drop something, the change in velocity is 10. It's going to go from 0 to 10. So I'm going to write 0, and then after a second, it's going to go 10. Average velocity is 5. You did that for 1 second, you went 5 meters. So there you go. So after 1 second, you went 5 meters in the y direction. If your speed in the x direction is 100, you're going to go 100 meters. So there you go. So even just looking at the equations, is there things that you can spot out? And definitely after 1 second, you should always do that. Any physics or dynamics problem, like if you can't tell what the hell is happening after 1 second, then that's truly, you're going to miss the fundamentals of what's going on. And that's why I always try to take a problem, especially if you can do something in a second that's tangible. Hell yeah, that's going to be the easiest thing, especially when your acceleration value is typically in units of meters per second. We don't typically change that seconds. We're not having acceleration in meters per second per picosecond, or even changing like those two parameters around. So hell yeah. Okay, sweet. All right, so we're done with this one. Part 5 is rearranging these. And thanks for joining me on this one. And hell yeah, there's the problem again. And booyah.